Hello, and welcome to this mini lecture on mathematical models. To begin, we identify a real-world problem. This could be general, for example, how do fluids flow through the subsurface? Or it could be more specific. For example, how long until contamination entering the ground at location X1 shows up in the aquifer located at X2. Once we have defined our questions, we can begin to identify variables and parameters that will impact the behavior of the system. For example, we might need to know the flow rate, hydraulic conductivity, the area, time, etc. As we start to build the mathematics that will enable us to answer our questions, we must begin with first principles to derive our governing equations. In hydrogeology, we typically start with conservation of mass or energy, but mass is easier to measure. We also utilize Darcy's law, the equation that states that discharge, the volume of fluid traversing a cross-sectional area per unit time, is equal to the hydraulic conductivity of the material multiplied by the change in head across the volume of interest multiplied by the cross-sectional area of the discharge outlet. These derivations necessarily make many simplifying assumptions. For example, we might assume that flow is homogeneous, isotropic, and steady state. Once we have identified our general equations and made the appropriate assumptions about the system under study, we have formulated our mathematical model. The next step is to identify the appropriate tools that we need to solve the problem. That could be as simple as utilizing our calculator or maybe Excel, but it could be more complicated and need to use computers or even supercomputers. Once we've figured out what we need to execute the math, we can simply solve the problems. We plug our specific values into each of the parameters in the model and solve the model. This enables us to calculate the time that flow will take to reach a location, what the discharge might be, any change in hydraulic head, or whatever it is that we're interested in learning more about. Once we have these numbers put out by the model, it's important to go check them against real-world data sets to make sure that our mathematical model is a good enough representation of reality to provide useful information. This stage is called model validation. However, in this class, we work with equations that have already been validated by others, and so we don't need to take this step. Instead, we can move on to visualizing the solution and drawing conclusions. In other words, what implications do the model results have for the real world? Depending on the results generated, we might want to go ask further questions. Or we might want to make changes to our model to see what would happen to the system under a variety of different scenarios. Mathematical models are powerful tools that enable us to learn new and important things about the world around us. They can be used to provide information and to tackle all sorts of problems. In the case of groundwater flow, these models are an essential part of building our understanding of a crucial natural resource that is simply impossible to lay eyes on. That concludes this mini tutorial on mathematical models.